today we'll do Python, and then we'll have a guest lecture on cloud computing. And homework 5 is due next week, I think next Tuesday. So you still have a week to do it. So 2 more sets of office hours if you need help. Projects, so yeah, midpoint, it's just the same as last week, but midpoint is in 2 weeks. How is everyone's project going? Have you guys written some code? Are you still lost? If someone doesn't know what their project is? Okay, great. Yeah, I saw that, and you're in my group, so it's better to know what your project is. All right, fine. So yeah, we'll have a hackathon next Thursday. So it'll be in a week and a couple of days from today. And we'll have food. We'll have VR demos. We'll have a bunch of other fun stuff for you to do. But you can also use that time to kind of work on your project, get some big stuff that you wanted to do out of the way. And we'll have another announcement about it. Yes, later in the week. It'll be in Siebel, room 2405. And then after the midterm presentations, we'll also do a midterm review session at some point before the CBTF midterm, so that you guys are ready for that. So yeah, that's kind of what the next few weeks will look like. But before we start with Python stuff for today, we looked at all of the submissions for homework 3 and homework 4. We found a few concerning things, which is that a lot of you are cheating, and that is not what we want you to do in this course, and definitely not in one of the first few courses that you take here at university. There will be classes in which you really want to cheat, and we want to make sure that you don't feel that way starting now. So please remember that it's not worth it. There are consequences, but for this class at least, we'll go easy for the first violation. You'll just have 20% of your grade on 1 or 2 homeworks, depending on what you cheated on, deducted. But if you do it again, there will be, it will go on your record, and there will be, a drop in a letter grade, blah, blah. So, if you have questions about something, or you think you cheated and you want to talk to someone about it, please do that. But I think Allegra's been talking to a few people about it already. So yeah, just remember, don't be that guy. All right, great. Cool. So today we'll do, I think it's Python first, and then micro lecture on cloud computing. But we're gonna have to wait for Allegra to show up because pretty sure she's doing the. So in the meantime, I guess you guys can fill out the attendance form. The code word for today is cloud. The link is in the Slack, so just go ahead and do it.
Okay, hey guys. Hello, hello to you. All right, so today we're going to be covering linked lists. So linked lists are a very important concept. They show up a lot in interviews. Has anybody here had an interview yet? Just raise your hand. I see someone surreptitiously, possibly raising her hand back there. Anyway, yeah. So if you're in an interview, like they might give you a linked list question and then ask you to do some manipulation. And sometimes the problems are a little bit tricky, but if you know what you're doing, then it'll be easy. Okay, so you can see here, it explains what a linked list is. It's basically, like it says, a list that has nodes that are linked together. So basically, each node can store different information, and then they're connected. So can somebody give me an example of like, why would you use this? Yeah.
Like for example, you can have like a reference, like for example, like a referral system. You can have like one person refers to the next person, and then refers to the next person. Like so, it forms like a chain or connection.
Yeah. So basically, yeah, that's the crux of it, right? Is that there's some sort of connection and order between the different nodes, and so having the links between them shows us how exactly those are related. Okay, yeah, so the key points here are that we have pointers and nodes. So the nodes are basically holding the data, and the pointers are indicating where that node leads to next. So you can see right here, in this notation, we've got something like this. So nodes 1, 2, 4, and 5, and they link together like this. Okay. And so then to keep track of where we actually are in the linked list and where things begin and end, it's basically we have a head and a tail. So the head will always point to the beginning of the linked list and the tail will point to the end. So that way you can know if you're iterating through it that you're at the beginning and then you'll know when you're at the end. Okay, so you can see here, it says that linked lists are, they're actually different from arrays, but in terms of arrays are actually more efficient. So why do you think that is? So you guys might not be super familiar with memory, but what, yeah, you back there.
Arrays take up like contiguous memory, so you know exactly where every element is, whereas linked lists allocate like wherever there's room, so you have to like traverse through the entire list to get to it.
Exactly, right? So the problem is that linked lists, the nodes can be stored anywhere, right? So we might have to jump around within memory. But with an array, it's right next to each other, so access is very fast. Okay, so we've got something like this, right? So an example, we can make a shopping list. So basically, what we can do is we can write this, like we can just have a piece of paper, and we can write all of our, all of the things that we need on that piece of paper, right? Or we can have a bunch of little sheets of paper and put them together. So basically, if you see here, our example, we only have 5 lines on our sheet of paper, right? So if these are the things that we want to buy, we have them here, right, on our paper. And then if we have this, if we transform this from one sheet of paper to a bunch of little sheets of paper that are connected together, we get something like this. So it starts with potato and then goes through lettuce, orange, homework 1 answers, 5 Bitcoins. So it's basically just saying like, okay, we can have all these things together in an array, or we can chop them up and have them actually link to each other. So it's basically the same thing, right? But they have advantages and disadvantages to each method. So like, for example, let's see here. So what happens is, let's say someone calls you and they say, okay, like, for example, my roommates, I don't know, they're obsessed with bananas, so that we have like 40,000 bananas in our apartment. So let's say they like contact me and they're like, oh, go buy bananas. Why would it be useful to have a linked list instead of an array for that? What is the advantage of a linked list over an array for adding elements? Yeah, back there. So the thing is that, yeah, with the array, we have to expand it and then put it there, right? So basically, it's time consuming and expensive to go get another piece of paper, like expand it to 6 lines and then put that thing there, right? So here they're using a microwave instead. So what they do is they get a new piece of paper, they expand it, and then they put it there, right? So it's very time consuming. It's not efficient. But if we're picturing this like a bunch of pieces of paper just taped together, then all we have to do is just add that, right? So all we do is say, okay, we have an extra thing here, it's a microwave, bananas, whatever you want. All we have to do is just attach it to it, right? And because it doesn't have to be the array, there's no array, it doesn't have to be expanded. So this can be anywhere in memory. And so it's very easy just to link them together. And then here's a good point here is that you might not know how many elements you have, right? So you don't want to keep resizing your array because that takes a long time because it has to go into memory, allocate more memory every single time you do this, and that's very time consuming. So if you do it this way, it just creates a node somewhere in memory and links it to the rest of your list, which is more efficient. Okay, so let's take a look at this. So if you have an array, and we want to insert like a number into the third element, right? What do you have to do? You have to make a space for that, right? So you guys probably know this already. So here we've got the third index, and then we have to move everything, and then we have to insert it, right? So that's a huge pain, because what we have to do is we have to allocate more space, we have to shift everything over, and we have to put that in the right spot. So it's a lot of work. However, if we just do an insertion, because we have pointers, what we can do is, like, as you can see here, we just swap pointers. So we can make a new node, and then we can just reset the pointers so they point to that. So 4's next pointer will point to that new element, and then the new node that we make, its next one will point to what 4's next pointer used to point to. So 4 used to point to 5, but we made a new pointer, right? Or sorry, we made a new node. So the new node was 1,000, so we take 4 and say, okay, 4's next is not 5 anymore, it's 1,000, and 1,000's next is now 5. So it's easy, right? Because it didn't take a lot of, we didn't have to expand anything, we just made a node in memory and we switched around the pointers. So yeah, so it says here, like, it looks like we moved stuff around, but we didn't, because this is all very, like, it's like a little puzzle. Like, you just stick the pieces in there and you rearrange the pointers so that there's a path to follow. So does anybody have any questions so far about this? Yeah, back there.
So if you want to insert something, like, when the actual process of changing the pointers is really fast, but doesn't it take a while to navigate to the place where you need to insert it in the first place? So, like, say you want to insert, like, pizza at the, like, 5 millionth element of your shopping list. You really need to go shopping. Then, like, actually inserting it is really fast. But first, if you go through the first 4,999 whatever elements, and then travel all of those nodes before you can get there to insert it. So how does it actually end up being an advantage?
Okay, yeah, so you're very correct. So basically, that's a disadvantage of a singly linked list. And so singly linked list means we only have links in one direction. So if I have 1, 2, 3, 4, they only go 1 to 2, 2 to 3, 3 to 4. It doesn't go the other way. So if you have a singly linked list and you want to get to, like, here we put it in the third position, right? You're right, we have to iterate through those until we get there. But the thing is, even so, it's not, we don't have to expand the memory. And so it's still like more, like we go up here. So if I go back up here to the array example, let's see. Yeah, so like we said, arrays are faster to access elements, but this one is, we don't have to expand the memory, which is important. Okay. Okay, so now we're going to talk about deletion, right? So with an array, somebody give me like a brief synopsis of how you would delete something in an array. how does it actually work? Yeah.
You have to like find the element you want to delete and then unlink it from the other one.
So in an array, right?
Oh, in an array?
Mm-hmm.
You magically make it disappear and have to ship all the other things back.
Yes, we have to get rid of it and like decrease the size, right? So let's say we already inserted this 1000 here, right? But we want to get rid of it. So what we do is we just shift everything to the left here. And so that's basically what you said. That's right. But then if we want to, so what did we talk about? List, we have list insertion. This should be list removal. So basically, yeah, list deletion. If we have this 1000 here, how do we actually get rid of it? So what we have to do is, and this is quite simple, right? So we iterate up to 4, right? And 4 points to 1000. So I've got this nice pointer here. And it's very easy for me to do this, to basically say, instead of this pointing to 1000, that node, I take this pointer and I say, go back and point to 5. Whoops, sorry, what just happened? All right, sorry about that. Okay, so yeah, so basically, when you delete something, it's really easy because we don't have to change the size for anything. All we do is we rearrange the pointer. So we pretend like 1000 never existed, and we just say, okay, 4, you link to 5 now. And this basically just ceased to exist. Okay, so a little bit before, we talked about runtime, and I think you guys talked about it when we had our theory lecture too. So this goes into a little bit more depth about how this actually works, right? So I'm going to take away this chart really quick. Hopefully you didn't memorize it really quick. But let's talk about runtime for these different operations. So for an array, what do you think the runtime is for insertion? Did someone say something? O of n? Yeah, right? So for an array, we have O of n. So why that is because we have to traverse to find the index that we want to insert into, right? And then if we need to expand the array, we also need to create more spaces. Okay, and then for a linked list, what is the runtime for an insert?
Consensus of row 1 is replies.
Yes, very, very right. So let's think about that for a second. So why that is because we have pointers. So we don't have to say like, if we want to insert something, we just can go ahead and say, okay, take this pointer, point it to something else, and then the new node points to the thing that was after it, yeah.
Does that runtime take into account the part where you have to get to that node before you actually do that?
That's a good point. So I think in this case, it's because,
I think it's like if you're given the data, you know where you're starting and just change something.
yeah, so it's not like we're traversing and then doing it. It's as if we are given a pointer and then saying, like, here's the index, here's a specific pointer, then insert one, and then that would be O of 1, right? Whereas if you were given an index and array and told to insert there, you'd have to move everything, which is a bigger problem, right? Okay, so then talking about deletion, the same for the array, right? So if you want to delete something, you have to get rid of it and shift everything. So that's O of n, right? But if you want to do it with a linked list, it's sort of the same thing, right? So we just say, okay, we're given this pointer to a node, and we just say, okay, get rid of this node and have that previous pointer point to the thing that was after the node that we deleted. So everything is still connected, we just got rid of the node that we didn't need anymore. Okay, and then element access is really important, right? So if we want to find something, if we want to get an element from an array, it's super easy, right? Because we just say, okay, I want array at 1, and it'll give me, in constant time, the value. But if I want to do that in a linked list, I actually have to traverse. The worst case is that I have to go all the way to the end to find what I'm looking for. Yeah, so you can see here, summary is basically, yeah, if you want to do write and delete, because these are like constant time operations, it's a lot faster with a linked list. But then you will realize later on that arrays are actually like pretty important for, they're efficient in a lot of other ways. So you'll be able to distinguish. Okay, so this is how you would go ahead and write your actual linked list. So we have a node class, and it contains data and next. So data is what our node contains, and next is the pointer that points to the next node. So let's go through this. All right, so here is our init function. So we initialize data to none and next node to none, and then what we're going to do is actually initialize the member variables so that that we construct this node. Okay, and then here, this function, what this is going to do is it sets, let's see, where's current linked list to one string. Okay, so it sets node to the one that we called it on. We have a string with our data, and then we set node equal to nodes next. So whatever node, let's see.
You're just traversing down.
Yeah, exactly.
Yeah.
So basically you're traversing, and you're getting all the, so here, you are putting it into a string, and then you are adding it into the buffer, and then you return the buffer. So you're getting everything from the nodes and returning it as like a string within the buffer. Okay, so yeah, so here are a bunch of functions that just print print different things with the nodes. Let's see. So if you use print node, you can print out the entire list. And we've got a bunch of examples here. So let's run this class. We'll run this. Okay, where did it go? Oh, here we go. All right, so linked list with only one element. So what we did here is we created linked list node with data 1, and we got it here. And then linked list with 2 elements, what we did is we set its next node to 2, right? And so now you can see we have 1, 2, and then 3 elements. And then here, when we're printing an intermediate one, we just started from next node and printed to the end. So that's why we just have 2 and 4 here. Okay. And then you can see here, we don't just have to have data like this, we also have these. Let's see, what is this function doing? So yeah, you can see the nodes are containing different things. So we have numbers, and then we have an array of strings, and then some more strings here. Okay, so does that make sense? Does anybody have any questions? Okay, yeah.
How do we delete the first element of this list? That's like the head.
Mm-hmm.
Like, I know, I get that we can like skip over others and delete other elements. Like, that's the second thing. Like, how do we?
Yeah, so if you wanted to delete the first element in a linked list, what you would do is you would take the head pointer, which is a separate thing. You would set that equal to the next node in the list, and then you would just, so if it's a singly linked list, then you wouldn't have to worry, because once you set head to the next node, it's sort of like we've just ignored the fact that there was a node before it. If you have something, I don't know if you know about doubly linked lists. If you have a doubly linked list, what we would do is we would say, okay, we're getting rid of the first node, so we set head to the second node, and then we set that second node's previous pointer to null, and that's just saying that's the first one. So it's just a lot of pointer manipulation, and you'll get really good at it in 225. Okay, so let's get another example here. A list to a linked list. So we're given a list, and we want to make it into a linked list, and return the head node, right? Okay. So here's some examples of what it's supposed to do. If we're given a list with these numbers, we want to have this, right? So 1 is the head, and then they all link together. And you can see the same thing here. Okay, so our parameters, list and norm, and then we have this here, returns. So head of the resultant linked list. Okay, so does anyone want to volunteer to actually try this? Yeah, you back there.
Should I come off?
Yeah, sure.
There's a node class defined, right?
Yeah, so you've got the node class here. Let me just run it again so that I make sure it's actually working. Okay. So you can go ahead and try to do this.
Hello. Can you all hear me? Yes, you can.
Yeah.
So what we need to do is we need to turn a list into a linked list. So I think the first most obvious thing to do would be to iterate through our list. Norm is the list that's passed into it, right? So let's start by just iterating through it. And then the naive implementation would just need to create a new node with every next equals none by default, so I don't need that. The first thing that we might do just to see what it does is create a node with a data value of x. So we just iterate through the list and create a node for every data value. The issue, of course, with this is we have no linkages, which defeats the purpose of having a linked list. We just have n discrete chunks that aren't linked to each other. So what we could do is in this for loop, we could worry about the next, or what I think is a better idea is to do it in 2 successive for loops, and then we have a we have a return list here that is actually a list of nodes, and then so what we're doing here now is we're creating a list of nodes. And the reason why I want to do it this way is because it's somewhat awkward, oftentimes in for loops, to deal with the edge cases at the beginning or the end, and then you get list out of bounds exceptions. And so it's easier just to first create a list of all of these nodes, and then we iterate through them again. Actually, it might just be easier to do this in one for loop, but I've already committed to this. And you can see my wonderful variable naming system of x. So then we'll iterate through these again. Yeah, it looks like what we're going to have to do. Am I allowed to use enumerate? Okay. I think I might do. I don't know if you guys have used enumerate before, but if you haven't, do, because it makes life so much easier. It basically just turns return list into a tuple with index and the value. So it makes it a lot easier to do for loops because you have both the index and the value at that particular index. I'm actually just going to condense this down into a single for loop and use enumerate. So then we can get rid of the second for loop down here. And we can get rid of this return list. Actually, let's keep it for now. So then I'm just going to think out loud a little bit here. We need to create each new node, and then its next value has to be a new node. Actually, I'm going to keep my previous organization structure, because the issue with trying to do it all in a single for loop is what does the next for loop have to be, right? If I did node x, and then secondary thing was node, node of norm index plus 1, this would create chunks of 2. So it wouldn't actually create a single linked list. What it would create is chunks of 2 linked lists, because if I did this on the second iteration, on the first iteration, it would create node x and node of the second value. So it would have a 2 long linked list. But then on the second iteration, it wouldn't create another element and add that to the end. What it would instead do is it would create a second 2 long linked list. So that's not what we want. So let's get rid of that. And it looks like what I was thinking we need to do is what we do need to do. Sorry, I'm typing with one hand here, so it takes a while. Return list. And so now what we do is we have however many nodes as we have in norm. Let's just say that norm, for our understanding's sake, that's not Java, is the numbers 0 through 4, or 0 through 3. So after we do this first for loop, what we have is we have a list of nodes. The first node has data 0, the second node has data 1, and the third node has data 2. The issue is that none of them are linked to each other. And the way that we link them to each other is by setting the next parameter. Also, do we have heads? No, we don't have heads. Well, I mean, there's no like head object. Because you
Make that in the first one.
yeah. But is there like a head variable?
No, it's just the set.
Okay, just curious.
That's linked. Yeah.
Yeah, sometimes with linked list, the way they structure it is with a linked list class, and then you have self.head and you set. But that is not the case. So instead, what we're going to do is we're going to say we have to check for this edge case. If index is equal to blank, return list. And the reason why I'm doing this is because if you think about the last test case, what I'm going to do is say return list index, or sorry, I could just say x dot next. Is it capital next or lowercase next? We'll go with lowercase next. It is lowercase next. So x dot next is equal to return list index plus 1. But then you guys can see you have the issue of the last element of the list is going to get an array out of bounds error. So we do that. We take care of that by just breaking if it is the last one. What?
The LEN return list is -1.
Oh yeah, thank you. That's a typo. So we take care of this edge case here, and then we have x.next equals return list, x plus 1, and then we will return list 0. So what we're returning here is the head, and then if we do this, is it command enter to run it? Oh, shift. Okay, and then if we call list to clean. Let's say the list 1, 2, 3. Let's first make sure there's no errors. We get a node, and then if we call that dot data, it should be 1. And if we do dot next dot data, this should give us 2. And it does indeed, and so on and so forth. So what we have here is we have a linked list, we have the head, and so we can iterate through if we wanted to. Yeah. Thanks.
All right, okay, yeah, awesome job. So if you guys are interested in taking a look at this, we'll go ahead and post these so you can play around with this. Yeah, but this is a really good example of getting this to work, so yeah. Okay, so that finishes up Python for today. If you have any questions, does anybody have any questions right now? Yeah. Add problems to the current homework? I'd have to ask the homework team. I'm not quite sure right now, but yeah, we'll see. But you can expect for linked list homework that we'll do ones sort of like this, but that they'll be sort of like interview ones. If you've ever done.
Yeah, the one due next week.
Yeah. Yeah. So linked lists aren't too tricky. Make sure you go to office hours if you need help, but it should be fine. All right. Yeah.
It will run tonight. It didn't run last night.
Yeah, it was scheduled.
All right. Okay. So now we're gonna have our micro lecture.
All right, cool, yeah. So we'll have the Marco lecture on cloud computing. I know some of you have midterms at 8:30, and if you need to leave at 8, yeah, linked lists are pretty cool. I'm sure you saw it on the homework. I had an interview today that I had to use linked lists for, and the use case was, so you had to, I think you had to check if a string was a palindrome. And so typically in Python you can just do a simple like one-line answer where you know, it's really simple. You can write it out. But the person wanted me to use a linked list to do it, and at the end she asked me why she asked me to use a linked list to do it, and then I thought about it for a while, and the only answer I could come up with was that it's faster, and that is true. So it's not necessarily faster, but it uses lesser memory. So fun fact. All right, cool. What's more in?
Hello. Hi, my name is Osmar Cornell. I'm going to be teaching you guys about cloud computing and clouds. So generally, when people think of clouds, they usually think of what is a cloud, right? So they usually think of these nice fluffy things, right, in the sky. But when we talk about cloud computing, we're usually talking about these, right? Big rooms filled with servers and just things lighting blue, right? They're still similar. They're more concrete. They're less fluffy. So in cloud computing and also in CS, we love buzzwords, right? So cloud computing, why and how? Why do we need cloud computing, and how do we do cloud computing? And the two answers are big data and big computers. As we get more data, right? Normal computers cannot process all the data all at once, and the way we compute things has to be different, because according to Moore's law, we get more processing and more everything. However, we've reached a peak where if we put too many transistors on a chip, things start to melt, so we need to add more CPUs, and then that stopped working, so what's next is get more computers. So let's start with the big question of how big is data, really? And does size matter? Right? Well, let's be honest, it's not about the size, right? But they do tend to be big. So that makes us think. Currently, or this was actually, I want to say a year ago, Google search has 5.2 billion daily searches. Facebook has 5.75 billion Facebook likes. There are around 656 million tweets. There should be more now. Instagram has 67 million posts every day. Facebook, there's 4.3 billion Facebook messages sent every day, and 4 million of hours of YouTube content posted every day. So that leads us to a large number of 2.5 quintillion bytes of new data every day, which is around 50,000 gigabytes per second, which is a lot of information and a lot to handle, and just using one for loop to like handle all that. So I'm not sure if they taught you big O notation, but that does not tend to, even some fast algorithm like O of n won't let you process all this data all at once. So a cute example right here is how we have, when we type into Google, we search computer, and we get lots of results all at once, really easily, really fast, in 0.7 seconds, right? On one computer, that would be impossible, but using many computers, a lot of processing units, we can achieve these levels of computation. So let's play a little game. This one's called Big Data or Pokemon. I will say a name and you guys have to guess if it's Big Data or if it's Pokemon. Spoink. Pokemon? Spoink is a Pokemon. Nice job, nice job. For those who know Pokemon, this might be too easy. Flink. Big Data? Cool. Flink is Big Data, yeah. Phoebus? Pokemon. Cool, okay. Phoebus is Pokemon, yeah. Impala. Impala's Big Data. Alright. Barbados? Pokemon. Okay. Barbados is Big Data. Yeah. Close. Azure? This was Pokemon. Nice. Why do they all sound like Pokemon? That's the big question now, right? Why do all big data sound like Pokemon? There's actually, have no answer for this. Anyways, this is the big data landscape in 2017. So again, a year ago, as you guys can see, many different products, many different platforms, many different companies using different softwares out there. Really cool stuff. Here we have some of the leading providers of cloud computing and cloud infrastructure. We have Microsoft and Google. Microsoft is a little bigger than Google. However, the biggest one is Amazon Web Services, which control a large majority of the internet. They control things like Netflix. So lots of the internet, if anything breaks in Amazon, the internet goes down. As I mentioned before, Netflix, Reddit, Spotify, and millions of others use Amazon AWS. And if it goes down, yeah, like the infamous S3 outage in February 2017. So, what happens when AWS goes down, right? Or inside AWS. And as you guys can see, AWS offers a big suite of products and different infrastructures that you can use to use your cloud computing skills. They allow virtual machines. They give you gigantic monsters of computers. They have GPUs, which are great for deep learning. Their pricing is pretty fixed, so it's pretty simple to use. I'm pretty sure students get a discount and you can use it for free in some areas. Azure, similar to AWS, they have some GPUs, not as many CPUs, not as much RAM as AWS. AWS is huge. But of course, hopefully we won't hit these limits. And then Google Compute Engine, which is currently the smallest of the three, provides VMs. Largest server is 96 vCPU and 624 gigabytes of RAM. And it provides custom-sized machines and cost is per minute. So if you want more precise pricing. So just one big computer isn't enough, like I mentioned. We have to have different computers that connect to each other, also known as the masters and the slaves. So let's take a look at GCP and how the infrastructure looks. And it looks something like this, where you have your master nodes, your slaves around it, and then you can connect to all the clients. And this is a little diagram of how one computer tells the other computers what to do, and therefore they can do things in parallel and get things done much faster than usual. So, now that we have multiple computers and lots of data, how do we write code? Do we just write it sequentially? Do we parallelize it on one computer? The answer is we change the whole mechanism of writing code. We no longer write things in parallel, but instead we use MapReduce, where basically we send information through a pipeline that maps everything out. It sorts it, and then it reduces it to one value. So, as I mentioned before, we have the map, and then we have the reduce, right? And this is a simple image of how it's done. You have your input, you pass it through the mapper breaks it up into components, which are sent into different computers. It's then sorted, and then it's reduced to the values that you're actually looking for. And this can all be done on different computers at different times. So it's really, really, really fast. It's a little different than parallel programming, but it's faster because you have more computers. Of course, for larger amounts of data. If you're trying to do this on a small amount of data, it's going to be much, much slower. So here we have an example of a simple for loop, where we loop through a range, and we add it to an array. And this is an example of how we do it when we map. As you guys can see, in each different chunk, we send a different part of the array, and we can append things. And here we have some Python built-in functions that are very easily used for mapping. Basically, you give it a function, and then you pass it your list, and map basically passes that function to every value in your list, as been shown. And then reduce, we can use lambda functions, which are just inline functions, anonymous things. Again, you have your reduce function, which is just takes in a function and takes in a list, and it calculates everything for you, giving you one value. And there we go. This is a more explicit reduce function. So, any questions before I go into the demo? No questions? Do you guys want to see a demo?
Yes.
Yeah.
Cool. So right here, I am logged into Google Compute Engine, right? This is my personal compute engine. You guys can easily get, I think, $300 of computing power through Google Cloud. And I've set up a little project that is supposed to, let's see if it works. So if I run my little project and I open it on my web preview, it's supposed to just be a little search bar that can find, that looks up all the, well, it searches all the words that match in, starting from the Wikipedia Black Panther movie page. So basically, it just searches through the words, sees if it's a match, counts it, and then goes through, I think, 10 other Wikipedia pages, starting through that page. So if I do, for example, Panther, I submit. As you guys can see, it takes a little while because this is just running on one computer, on one server. Everything is just one thing, so it's pretty slow. However, using Kubernetes and Docker, we can, basically what Docker does is it encapsulates the program into this little container that we can, this lightweight container that we can handle much easier, and we can program to run whenever we want and run whichever environment we want. And we're using Kubernetes to handle all the different containers, basically telling the Dockers when to run and what to run on, right? So if we run, let's see. So this is my Docker. As you guys can see, it's a similar thing, except that it's running on this lightweight container. And now for my Kubernetes, I think I currently ran into an issue where when I created Kubernetes pods, they were not able to upload the image correctly. So I'm not sure if I would be able to solve that just now. But basically, all you have to do is, to work with Docker and Kubernetes, you create just 3 different files. Docker will be for your container, which tells the Docker container how to run your application. Deploy YML for Kubernetes, which tells Kubernetes how to deploy your container from Docker. And your ingress YML, which tells the Kubernetes how to allow people to view your application. Currently, I think it's my deploy that's broken because it's not pulling the image correctly. Let's see if I can get it working. This should be completely free because I'm using the free tier. Of course, if you get your 300 credits, you can use them and you shouldn't be worrying about that. But yeah, otherwise what you can do is just run it for a little while and then close it down. You just want to test it. So let's see if it worked. What is Kubernetes? So Kubernetes, like I mentioned before, is orchestration, container orchestration software, which basically tells how to control your containers, right? Because the reason why you want to have containers is due to the fact that not everyone is running on the same environment, right? Some people have Windows, some people use Linux, other people use Mac, and Docker makes it very simple to create a lightweight container where you can run it anywhere. And then once you want to run it anywhere, right, that's one checkmark solved. However, you're still running a bunch of applications separately, and it's not like normal programming where you can easily just create another file and call the functions of another file just to talk to it, right? You need something bigger to control how the containers talk to each other. Does that make sense? Answer your question? All right, let's see if this works, and otherwise, I'm not sure. Yeah, I think it did not work. I'm pulling my images. Yeah. Alright, yeah. It's not pulling my images, and I don't know why. Demo something, right? Alright, that's it. That's it from me. Thank you.
All right, awesome. So yeah, it is 8 o'clock, so you guys are free to go. Make sure you fill out the attendance form and get working on homework 5 due next week. Awesome, thanks.